What's up guys, and welcome to this video on question 6 of the 2017 supplementary exam. This question has to do with gravitational fields and electric fields. Okay, so let's get straight into the question. A spacecraft on a mission to explore the outer solar system was between Jupiter and Saturn at the distances shown, and the masses are also given. The mass of Jupiter is 1.9 times 10 to the 27 kilograms, and the mass of Saturn is 5.7 times 10 to the 26 kilograms. Okay, and we have a nice picture as well as some distances and where the craft is. Okay, so question 6.1.1 is a definition. Okay, I will give you the definition, but I'm not going to write it out because it is a very long definition. But essentially, okay, so state Newton's law of gravitation, of universal gravitation. Okay, so basically it goes that every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distances between their centers. Okay, basically from this definition we derive the equation that the force is equals to a constant, the gravitational constant, times mass 1 times mass 2 over the center distance squared. Okay, basically that is what we get from that definition. And then we also given the mass of the spacecraft as 2.2 times 10 to the 3 kilograms. Okay, so 6.1.2. Okay, so it says calculate the magnitude of the force that Jupiter exerts on the spacecraft at the position. Okay, so basically we can say that the force that Jupiter exerts is going to be equal to the gravitational constant times the mass of Jupiter. Let's go with simple J, times the mass of the spacecraft over the center distance between Jupiter and the spacecraft squared. Okay, so the gravitational constant is equal to 6,7 times 10 to the minus 11 times the mass of Jupiter was given as 1.9 times 10 to the 27. Okay, the mass of the spacecraft was given in the question as 2.2 times 10 to the 3, and the center distance would be this distance right here, which is 3.9 times 10 to the 11 meters, and all of that is going to get squared. Okay, and we get that the force exerted on Jupiter is equal to 1.84 times 10 to the minus 3 newtons. Okay, and we get 3 marks for that. Question 6.1.3 says calculate the magnitude of the acceleration experienced by the spacecraft at this position. Okay, so let's start off with a free body diagram. Okay, so the free body diagram would look like something like this. This is the spacecraft. Okay, so Jupiter is pulling it. This said magnitude, that's why we didn't give it a direction, but if we did give a direction, this would be in the direction, let's do that, left. Okay, and then so that, let's say, is force from Jupiter, and then in the opposite direction we have Jupiter pulling it that way and we have Saturn pulling it that way, so force of Saturn. So basically what we need to do to calculate the acceleration, we're going to use the formula F net is equal to ma, and that gives us our acceleration, but we need to know the F net. So the F net part, we've already calculated force due to Jupiter, so we need to work out force due to Saturn, which is equal to the gravitational constant, the mass of the Saturn, sat times the mass of the spacecraft over the distance between Saturn and the spacecraft squared. Okay, so that's 6.7 times 10 to the minus 11 times the mass of Saturn, which was given as 5.7 times 10 to the 26. Okay, and then we're going to multiply that again by the spacecraft times 10 to the 3 all over the distance, which is given in the diagram as 4.2 times 10 to the 11, and we're going to square that. Okay, and we get force exerted by Saturn on the spacecraft. Let's just say sat, okay, is equal to, if we put that into our calculator, we get a force of 4.76 times 10 to the minus 4 newtons, and this time the direction is right. Okay, so basically the left force, or the force leftwards, so the force exerted by Jupiter is greater than the force exerted by Saturn. So basically spacecraft will move left. Okay, so I'm going to take the left direction as positive when we take the F net is equal to MA. I'm going to take, or we can say, the sum of the forces is equal to mass times acceleration, and I'm going to take the left direction as being positive. Okay, so the sum of the forces is going to be force of Saturn minus force of, sorry, that is a mistake. Sorry, the force due to Jupiter is greater than. Okay, so it's moving right. No, it's moving left. That's correct. So it's moving left. Okay, so again, so let's say force due to Jupiter minus force of Saturn is equal to the mass of the spacecraft times the acceleration. Okay, we know these values. We've calculated them, so it's 1,84 times 10 to the minus 3 minus 4.76 times 10 to the minus 4 is equal to the mass of the spacecraft, which is 2.2 times 10 to the 3 times the acceleration. Okay, the only unknown here is the acceleration, and this minus sign comes up because it's acting in the opposite direction, basically. So what we get is, if we calculate the acceleration, we get an acceleration of 6.2 times 10 to the minus 7 meters per second squared. Okay, and again, I think it asks for the magnitude of the acceleration, so we don't actually care about the direction, but if we did, it would be left. Okay, so just to clarify, because I did make a bit of a mistake, basically the force exerted by Jupiter on the spacecraft was greater than the force exerted by Saturn, and so Jupiter is on the left, so this force is bigger. So let's draw it in. So our force there was bigger, so our spacecraft will move towards the left, and we did a sum of our forces to get that. Okay, so I hope that made sense to you guys. Okay, so, and we get 6 marks for that. Okay, the reason for the 6 marks is because we have to calculate the force exerted by Saturn first. Okay, yeah. Okay, that question's done. So we can go on to 6.2. A small metal sphere has a charge of positive 5 nanocoulombs. The electric field is measured to have a magnitude of 312,500 newtons per coulomb at an unknown distance from the charge. Okay, so we're starting off with the definition. 6.2.1 is a definition. Okay, it's a short one. So define electric field. So electric field is the force per unit positive charge. Okay, the key word being positive charge. Okay, so 6.2.2. So calculate the distance from the charge where the electric field strength was measured. So we're looking for the distance. Okay, so if we look at our formula sheet, we can get the equation because we have the field electric field strength and we have the charge of the sphere, we can use the equation E is equal to K Q over R squared. Okay, and K is our constant, so we have E, this would be E, so E is equal to 312,500 is equals to our constant K, which is 9 times 10 to the 9. Q is the charge which we was given, which is 5 times 10 to the minus 9, and that is because of the nano part of the coulombs, and that's all over R squared. Okay, so the only unknown here is R, so we can solve for R. Okay, so R is equal to 0.012 meters. Okay, and that would be the final answer, and we get ourselves 3 marks. Okay, so overall not a very long question, 16 marks, and I think I got through it fairly quickly, even though I made a small mistake. Yeah, so yeah, I hope you guys were able to follow this. Pretty interesting question. Let's put this in brackets because it didn't ask for it. Yeah, so thanks for watching, guys. Yeah.